Welcome students to AP Chemistry, Unit 1, Atomic Structure and Properties. Today we'll be going over moles and molar mass, Unit 1.1. A mole is a word that represents a number, like a dozen represents 12 and a pair represents 2. A mole represents 6 sextillion. It's used to count the number of particles or molecules in a substance. 1 mole is 6 sextillion, or 6 times 10 to the 23rd. And we can use that conversion as we would use any other conversion. So I can convert from moles into molecules, atoms, particles, ionicals, any of those substances. So if I have half a mole of oxygen molecules, I can convert that into molecules using the conversion. For every 1 mole, I have 6.02 times 10 to the 23rd molecules. Moles cancel out, and I'm left with molecules of oxygen. So I would find that half a mole is 3.01 times 10 to the 23rd molecules. Or if I have atoms, I can tell how many moles that is. If I have 1.81 times 10 to the 24th atoms of gold, I can convert atoms of gold into moles. For every 6.02 times 10 to the 23rd atoms, I have 1 mole. Atoms cancel out, and I'm left with moles. So I find that this is approximately 3 moles of gold. Now, when tracking how many atoms are in a molecule, or tracking how many atoms are in a mole of molecules, we'll need to look also at the subscripts. Subscripts apply to what is directly in front of them. So for example, the formula for water, H2O, that 2 denotes that there are 2 hydrogen atoms for every 1 oxygen atom. So if I have 1 mole of water molecules, that means that I have 2 moles of hydrogen atoms and 1 mole of oxygen atoms. Coefficients can often be seen as how many moles are in a balanced equation. So when I write 2 H2Os, that means that there are 2 moles of water in this formula, meaning that there would be 4 moles of hydrogen atoms and 2 moles of oxygen atoms. Now, when we use whole numbers like this, it's pretty straightforward, but if we were to use fractions, it would still be the same idea. So how many atoms of each element are in 0.002 moles of sulfuric acid? We are simply going to say, oh, I have 2.002 moles of this whole substance. So for the formula sulfuric acid, there is hydrogen, sulfur, and oxygen atoms present. Our formula for sulfuric acid has 2 hydrogens in it. So the number of moles would be twice as much, meaning that there are 0.004 moles of hydrogen in our 0.002 mole sample. And then it's a simple matter of converting moles into atoms. There are 6.022 times 10 to the 23rd atoms in every 1 mole. The moles cancel out, leaving me with how many atoms of hydrogen are present. So we find that there are 2.41 times 10 to the 21st atoms of hydrogen in our sample. Sulfuric acid only has 1 sulfur atom in its formula, so if we had 0.002 moles, that would be 1 times 0.002 moles. So we have 0.002 moles of sulfur. And this same conversion can be used. Moles cancel moles, leaving me with atoms of sulfur present. So in our 0.002 moles of sulfuric acid, there are 1.2 times 10 to the 21st atoms of sulfur. Lastly, for oxygen, sulfuric acid contains 4 oxygens, so 4 times 0.002 tells us that we have 0.008 moles of oxygen, which would mean that there are 4.8 times 10 to the 21st moles of oxygen present in our sample. Moles are the central unit of chemistry. When in doubt, if you ever are stuck on a problem, you will always be safe to figure out how many moles are present. So if ever you are lost on a problem, please figure out how many moles are present, because moles are where you should be most comfortable in this class, because from moles we can go to any other unit. Now, where the mole comes from is actually a very long assorted history. We used to look at atoms based on their relative masses to one another in a sample. So hydrogen being the smallest atom, we used to use things relative to hydrogen based on the work of Dalton. The problem was the hydrogen does not bond with everything on the periodic table. Hydrogen can be reactive in its acidic form, but hydrogen does not react very well with metals very often. And so, after a while, we started using oxygen, because oxygen bonds with most chemicals on the periodic table because it oxidizes. Oxygen has a relative mass of 16 relative to other elements. And we use that set number of 16 to find the mass of other elements. So 1/16 of an oxygen was considered hydrogen, and everything else was based off of that ratio. However, in the early 20th century, it was discovered that oxygen comes in a variety of flavors. It can be heavier or lighter than 16, which led to some numbers in some experiments being off. So in the 60s, the International Union of Pure and Applied Chemistry, or IUPAC for short, started to look at what could we use to standardize this across the planet. And so it was agreed that they would say the mass of a carbon-12 atom was considered the standard, because carbon is mostly carbon-12. So the mass of a carbon-12 atom was said to be exactly 12. And if you had 12 grams of carbon-12, how many atoms was that? Well, that's where this 6.022 times 10 to the 23rd comes from. 12 grams of carbon-12 contains 6 sextillion atoms, and it's the basis for our mole. So the masses on the periodic table can be seen as atomic mass units, but they can also be seen as the number of grams in 1 mole. So on the periodic table, if you look at carbon, whose atomic mass is 12.01, that 01 is from the isotopes of carbon that are slightly heavier or lighter than carbon-12. That 12.01 can be seen as the mass of an atom of carbon on average in AMUs, but it can also be seen as the mass of 1 mole of carbon. So if you collect 12.01 grams of carbon, you have found 1 mole of carbon. This is where the idea of a molar mass comes from. It is the mass of 1 mole of an element or compound. In the terms of elements, it's just taken off the periodic table as we just did with carbon, but with compounds, you add up the average atomic masses of all the elements present. So for water, 1 oxygen and 2 hydrogens, you add up 1 oxygen and 2 hydrogens. So 16 plus 1 plus 1. If you collect 18 grams of water, you have found 1 mole of water. There are 6 sextillion atoms present. 1 mole of water is approximately a teaspoon. Or methane gas, which is 1 carbon and 4 hydrogens. So if you add up the mass of 1 carbon, 12, and 4 hydrogens, 1 times 4 is 4, you get that there are 16 grams for every 1 mole of methane. So let's do some of these. If I have 9 grams of water, how many moles is that? Well, I can go from grams to moles using the molar masses off the periodic table. For every 1 mole of water, there are some number of grams. So this is where the molar mass of water would go. Molar mass of water would be 2 hydrogens and an oxygen, so that's 2 times 1 plus 16, so 18 grams for each mole. So 9 divided by 18, this is approximately a half a mole of water. If you have 2 moles of methane, what is the mass of 2 moles of methane? Well, 2 moles of methane, I can convert from moles to grams using the molar masses off the periodic table. For every 1 mole, there are some number of grams of methane. So the molar mass of methane would go here. So 1 carbon and 4 hydrogens. So that would be 12 plus 4 times 1, which is 16. So our 2 mole sample would have a mass of 32 grams. A cup of Starbucks coffee contains 38 grams of sugar, which is sucrose. How many moles of sugar are in the cup of coffee? And how many molecules would that be? Well, we have 36 grams of sucrose. In order to figure out how many moles that is, we'll convert from grams to moles using the molar mass sucrose. Because for some number of grams, we have 1 mole. So sucrose is 12 carbons and 22 hydrogens and 11 oxygens. So that would be 12 times 12 plus 22 times 1 plus 11 times 16 for a grand total of 342 grams for every 1 mole. So 36 divided by 342, there are 0.105 grams of sucrose in a cup of Starbucks coffee. If we wanted to convert that into molecules, we could actually expand this dimensional analysis out, because for every 1 mole, there are 6.022 times 10 to the 23rd molecules. And now molecules cancel out, just as grams cancel out. So if we take our answer and we multiply by Avogadro's number, we get that there are 6.33 times 10 to the 22nd molecules of sucrose in a cup of Starbucks coffee. And with that being said, you are now able to do page 17 in your packet. Go ahead and pause the video and do page 17. For number 11, you might want this hint. What are the units for molar mass? And mathematically, what would you have to do to end up with those units? So that's your hint for number 11. Go ahead again, pause the video and do page 17. When talking about the molar mass of a substance, we're using the decimal point numbers off the periodic table. Those decimal points are the average atomic mass of all the known isotopes of an element. So all atoms that have the same number of protons are the same element. Anything with 6 protons is automatically a carbon. Anything with 8 protons would be an oxygen. However, not all oxygens and carbons are the same. they can have different masses. So in order to figure out the mass of an individual atom or individual atoms within a sample, we use mass spectrometers. A mass spectrometer takes a sample, heats it into a gas form, and passes it through a magnetic field. The magnetic field warps the path of that gas so that lighter elements hit a detection plate differently than heavier elements. And we look at the mass of those individual atoms to determine their individual makeups. So if we have the mass of some atom of carbon-13 in grams, and we divide by the mass of carbon-12, which is the basis for our average atomic mass units, we get some ratio. We define carbon-12 as 12 atomic mass units, so if we multiply that ratio by 12, we get the individual mass of our sample of carbon-13. Now, carbon-13 is different from carbon-12 because their masses are different. The carbon-13 is an isotope of carbon. Isotopes are the same element. They all have the same number of protons, and if they're neutral, the same number of electrons. So they have the same chemical and physical properties. However, where isotopes are different is that they can have different masses based on the number of neutrons they have. So for example, the most common form of hydrogen is protium, a single proton with a single electron. However, hydrogen comes in other flavors. Hydrogen can be a little heavier by having one proton and one neutron for a mass of 2. This is known as deuterium. It is the same as hydrogen, has the same chemical and physical properties, it's just slightly heavier. And in very rare cases, a hydrogen atom can have 2 neutrons and a proton for a mass of 3 atomic mass units known as tritium. Exceedingly rare, but it is an isotope of hydrogen. Now, if you take a weighted average of all the isotopes of an element, you end up with its average atomic mass. And that is the decimal point number you see on the periodic table. It is a weighted average of all the known isotopes. On the periodic table, you will see some average atomic masses in parentheses. For example, neptunium has an average atomic mass of 237, but it's in parentheses. That is because there are no stable atoms of neptunium. It decays rapidly, and so we have a theoretical mass, but we cannot find an average based on the isotopes present. So to find the average atomic mass, it's a weighted average. Not all masses are weighted the same. They're weighted based on their percent abundance. Within a sample, what percentage of that sample is one isotope versus what percentage of that sample is a different isotope. So we will take the percent abundance of one mass and multiply by the mass of that isotope. And then we add to it the mass of the second isotope times its percent abundance. That percent abundance weights the average. So if you have something whose average atomic mass comes out to be 15.9996, like oxygen, you could probably assume that most of oxygen is oxygen-16, and then you got a couple few atoms that are lighter, maybe a few that are heavier, but most of the sample is probably oxygen-16. It's probably had the biggest percent abundance. Now that's a general rule of thumb. It's not always true. For example, bromine's average atomic mass is 79.9, so you would say, oh, well, bromine 80 has to be the most abundant. But that's not true. In fact, there's no such thing as bromine 80. Bromine 80 is highly unstable. Only bromine 79 and bromine 81 exist. They exist almost 50% of the time, and so averaged together, they come out to be very close to 80. Now on the AP exam, you will need to be able to calculate the average atomic mass using the percent abundance. So find example 4 in your packet. Example 4 says that copper in a sample has 2 masses, 63 and 65. Using the percent abundance from the sample, find the average atomic mass. So our average atomic mass is going to be, if we take the mass of 63 and multiply by the percent of 63 and add to it the mass of 65 and multiply by the percent of 65. And they want us to use the actual masses off the mass spectrometer. So we're not going to use 63, we're going to use 62.93 for the mass of 63. The percent abundance, we're going to use 69.09%. Now, percent, if you did not know, the word percent is actually an abbreviation, percenti, meaning for every 100. This is a mathematical operator. It simply means divided by 100 for each 100. So you won't put 69.09 here, you would put 69.09 for each 100. So we're going to take that and add to it the mass of 65, so 64.93, times the percent of 65, 30.91 for each 100. So the average atomic mass of our copper sample here comes out to be 62.93 times 69.09, 43.478 plus 20.069. So the average atomic mass from our sample comes out to be 63.55 atomic mass units, or 63.55 grams for every 1 mole. And yes, you could find that on the periodic table. The periodic table would provide a good check for an element that is known. But again, you should calculate it based off of the problem because not all samples are the same. We can use the average atomic mass off the periodic table to find the percent abundance. So argon has 2 different isotopes, 39 and 40. Given the average atomic mass of the periodic table for argon, what is the percent abundance of each isotope? So average atomic mass would be the mass of argon 39 times the percent of 39 plus the mass of 40 times the percent of 40. And while we know this value and we know this value, we also know this to be 39.948, given off the periodic table. The percentages we do not know. Now, mathematically, when you don't know a percentage, you assign it a variable. So let's call this x, and we'll call this y. So now you have 2 variable math. You've got 39x plus 40y has to equal 39.9. You can't solve 2 variables. You have to get one alone. You have to isolate one. But what do we know about percentages? A percentage is out of 100 for each 100, meaning x out of 100 plus y out of 100 has to equal 100, or x plus y has to be 1. Meaning I could use this known definite value has to equal 100 to figure out one or the other. So I could rearrange this and say, okay, or 1 minus x has to be y. And then I could plug that in. I could substitute y for 1 minus x. Because after all, y has to equal 1 minus x. And now it's straightforward algebra. 39x plus 40 times 1 minus x has to equal 39. We can distribute. We get 40 minus 40x plus 39x has to equal 39.948. Combining like terms, we get negative x plus 40 equals 39.948. So I get a negative 0.052 equals negative x. Divide by negative 1 on both sides to get that x is 0.052, or the percent of 39 would be 5.2% by multiplying by 100. By subtraction, the percent that's 40 would be 100 minus x. So the percent 40 would be 94.8%. With that being said, you're able to do page 18 in your packet. Please pause the video, do page 18. For any problem in which a mass is given, please use the given mass. Do not use the rounded average. Do not use the rounded atomic masses that you see in isotope notation. Please use the decimal points in the problem. And with that being said, we are done with Unit 1.1. Please remember to do your Unit 1.1 personal progress checks in the AP classroom. These are graded for completion, so as long as you get it done before the day of the test, I will be happy and you will get your 100. But it will allow you to see where you are deficient or where you are succeeding in this subunit. Next class, we will be looking at elemental analysis, determining the empirical and molecular formula of compounds.